All right, let's dive into something truly epic. We're going on a quest to understand one of the most ambitious ideas in all of science, the attempt to create a complete atlas, a full map of every single possible shape our universe could be.
Seriously, just think about that for a second. What if we could actually write down a list of every conceivable three-dimensional shape a universe could take? It sounds like something straight out of science fiction, right? But it's actually one of the deepest questions in mathematics. And the story of how it finally got solved is just, well, it's absolutely mind-blowing.
So, how in the world do you even begin to tackle a problem that big? Well, with most of these huge, complex problems, a good first step is to look at a simpler version. So, let's start by dropping a dimension and looking at 2D. Now, for two-dimensional surfaces, this problem was actually cracked a long, long time ago. Mathematicians proved that any 2D surface, it doesn't matter how you stretch it or bend it, is basically one of just three types: a sphere, a totally flat plane, or a weird saddle-shaped thing called a hyperbolic plane. That's it, a perfect, complete list. But the moment you add that third dimension, oh man, the complexity just explodes. It is a completely different ballgame. The official term for one of these potential 3D universe shapes is a three-manifold. And all that really means is it's a space where, if you could zoom in on any single point, it would look just like the normal, everyday 3D world around you. The real trick, the cosmic mystery, is figuring out how all those little points connect to each other on a massive universe-sized scale. For decades, trying to classify all these three manifolds just seemed totally impossible. It was a mathematical dead end. That is, until the 1980s, when this brilliant mathematician named William Thurston came along with an idea that was... Well, it was completely revolutionary. See, Thurston's genius was to just stop trying to force one single geometric label onto these messy, tangled-up shapes. He basically said, hey, instead of doing that, what if we find the natural seams inside the shape and just cut it up? The idea was that any ridiculously complicated three-manifold could be broken down into a set of fundamental building blocks, and those little blocks would have clean, simple, perfect geometries.
The process itself is just beautiful in its simplicity. So first you start with your messy, complicated shape. Then you find these natural seams inside of it. They happen to be donut-shaped surfaces called tori, and you slice right along them. And what you're left with is a collection of fundamental pieces, and each one of those pieces has its own perfect, understandable geometric structure.
So that leads to the big question. What are these fundamental pieces? If you can chop up any shape, how many different types of building blocks are you going to end up with? An infinite number? 1,000? 100? The answer was just stunning. Just 8. That's it. All the infinite, mind-bending complexity of three-dimensional space could be understood as just different combinations of 8 fundamental geometric types. This was the core of his geometrization conjecture. It was like he'd found a Rosetta Stone for the shape of space itself. The three most famous of these 8 flavors of space are spherical, Euclidean, and hyperbolic. You've got spherical, which is finite and curves in on itself, kind of like the surface of a ball. Then there's Euclidean, which is just the flat, normal space we all learned about in school. And hyperbolic is this wild, infinitely expanding space. The other 5 are a bit more exotic, but the principle is the same. These 8 shapes are the Lego bricks for building any possible 3D universe. Now, here's the thing about math. Having a brilliant idea, a conjecture, is one thing. But proving that it works in every single possible case, that is a whole other beast. Thurston had drawn the map, but now someone had to prove that the map was actually correct, and that was going to require some brand new tools. The key tool came from another mathematician, Richard Hamilton, and it's called the Ricci flow. The best way to think about it is like this. Imagine your 3D shape has all these lumpy and bumpy parts, like hot spots and cold spots, representing how much it curves. The Ricci flow is a process that lets all that heat spread out and even out, smoothing the shape over time and hopefully revealing the perfect underlined geometry that Thurston predicted. It was a genius approach, but it had a nasty habit of running into problems and creating singularities. So, the stage was set. Back in 1982, we had the conjecture and we had a tool that looked like it could solve it. But then, Nothing. For 2 decades, the problem was just stuck. The best mathematicians on the planet threw themselves at it, but nobody could quite figure out how to control the Ricci flow. The grand quest just stalled out. And then, in 2003, out of nowhere, everything changed.
The solution didn't come from a big paper at Harvard or a fancy conference. It came from a quiet, reclusive Russian mathematician who, for all intents and purposes, had vanished from the academic world. Grigori Perelman.
Perelman, working completely by himself in St. Petersburg, didn't submit his world-changing work to some prestigious journal. He didn't call a press conference. He just uploaded a few papers to a public website, an online archive where scientists post their research. And he just walked away. That's it.
3. In just 3 short papers, he laid out the complete solution to one of the deepest, most difficult problems in the history of mathematics.
And he submitted them to exactly 0 academic journals for peer review. He just left his masterpiece on the internet's doorstep for anyone to find. It took the entire global math community years to check it all, but the conclusion was undeniable. He'd done it. He had finally tamed the Ricci flow and proved the geometrization conjecture.
And if you think that's wild, the story only gets stranger. Perelman was offered the Fields Medal, which is like the Nobel Prize for math, and a $1 million prize. He turned them both down, flat out refused. He said he wasn't interested in fame or money, and with that, he cemented his place as one of the most brilliant and mysterious figures in the history of science.
But okay, Perelman's incredible personal story aside, what did his proof actually mean for math, for science, for our understanding of the universe?
It meant that the decades-long, seemingly impossible quest was finally over. Thurston's beautiful, audacious idea was no longer just a conjecture. It was a proven fact of our reality. It's now called the geometrization theorem. The complete map of 3D space was finished.
The fallout from this was immense. As a little side effect, the proof also solved the super famous Poincaré conjecture, a 100-year-old problem that was one of the biggest open questions in all of math. And for physicists and cosmologists, this gives us a fundamental toolkit, a complete instruction manual for modeling the possible shape of our very own universe.
So that leaves us with this one last incredible thought. We've done it. We have the complete map for 3 dimensions. But what about 4 dimensions, or the 10 or 11 dimensions that string theory talks about? The math gets exponentially harder, for sure, but the human drive to map reality, to understand the shape of everything, that never really ends. What other hidden cosmic maps are just waiting out there for someone to draw?